Yeah, welcome to this session. I will talk about trash. So I hope you will enjoy it. It's about memory management in the JVM. And I guess all of you are Java developers. Yes? Okay. Okay, let's start. So my name is Gerrit Grunwald. I'm working for Azul as a senior developer advocate. I'm also running a Java user group and other stuff that's not that important. So memory management in the JVM, right? It's automatic, correct? So why care? Right. Who is actively setting a garbage collector in his production environment? Okay, a few. The rest just choose the automatic one, the default, right? Someone else. Okay, good. So in principle, it has an impact. So you should care at least a little bit. So because it has an impact on the application performance, responsiveness, and also system requirements, right? So, and in this session, I will just give you a little refreshment about how it works. Try to explain the algorithms as simple as possible, because sometimes that really can help fixing problems. So in the JVM, we have the stack, heap, and meter space, where the stack is thread-based, so each thread comes with a stack frame, and this grows and shrinks dynamically, and it more or less just contains primitives and references, the stack frame. And it's local access, so it's thread safe, so we don't do any garbage collection in this part. And then we have the heap, where we store the actual objects, right? And this one is shared access, so it's not thread safe, and we need to do garbage collection in this one. We will see why. And then there is a so-called meter space, which contains class metadata, constant pool, method, bytecode, and so on. So in principle, everything the JVM needs to work with classes. And this is not part of this session. So we mainly will focus on the heap and the stack frames. Okay, so I created a little piece of code to give you an idea how it works. You see we have a record person. I have 3 or 4 instances here, and then I have a list of persons that keep these instances. So I print out the first one, my name, all good. This is the stack frame for this piece of code. For this thread, we have the stack frame, which contains the references to all of these objects that I created. And the objects themselves you will find in the heap, right? So there's the memory which is allocated, and you see that the references point to the objects on the heap. So that means you see the 4 objects, you see the list, and in the list on the heap you see there's an internal reference to the same objects, right? These objects are all reachable. That means you can reach them from the stack frame following the references, you can reach them on the heap. So if I now set P1 to null, then if I would print out P1, I won't get any result back. But because it's still referenced by the list, the object is still reachable, right? The reference is gone to the object directly from the stack frame, but via the list you still have the reference to the object. You can ask for the list, or the persons get 0, and then you will get the same result as before. So the object is still on the heap. When I now remove the list by setting it to null, the reference is gone, and so I can't reach it anymore, right? So that means in this case, only the 3 middle ones are live objects. You can reach them from the stack frame, but you can't reach the list even if it's still on the heap. So the objects will allocate space on the heap, but you can't reach them anymore. So this is more or less dereferenced dead objects, right? Lying around, and in the end that means this is garbage. And how to get rid of garbage? You need garbage collection. That's the main idea, because otherwise we will fill up the heap, and then it's at one point it's gone, and then you get an out-of-memory exception. All right, so garbage collection, just as a short introduction, it's a form of automatic memory management. There's also automatic reference counting in other languages, like Swift, for example, which is just a different approach of doing it. It identifies and reclaims no longer used memory, ensures efficient memory utilization, and in principle, this is the most important part. It frees you from doing something like malloc and free, as you might know it from C. And we have to split it in different phases, Because if we talk about precise collectors, and this is just all the collectors in the JVM are precise collectors, and there are also so-called conservative collectors, but we will only talk precise ones. And we have different phases. First of all, we have a so-called tracing phase. That means this is the phase where we try to find the live objects on the heap. And then there's a freeing phase where we have to free all the dead objects from the heap. And then there's also compaction, where we have to compact the heap. So short question, who's old enough to remember Windows 3.11? Okay, that's good. You always remember this defragmentation thing of the hard drive? Okay, this is exactly what we are going through now, because it's very much the same. To give you an idea, because who heard about Stop the World? Yeah, not all of you, right? So that's why I'm explaining it. When we talk about Stop the World, when we talk about garbage collection, then it means we halt all the application threads. So usually it's like this. We have application threads running, then we send a save point signal from the JVM to these threads, and then they will stop, right? And once all the threads are stopped and in a safe state, then we can do the garbage collection. Once the garbage collection is done, then we can continue with the application threads. So this is when we talk about Stop the World, this is the pause that you see in orange here, where we do the garbage collection itself. And this could be a problem, right? Because this pause, depending on the collector that you choose and also on the kind of application that you're using, then it can lead to stops in the range of seconds, like 10 seconds, if you have a big application. And that means in this 10 seconds, your application just won't respond at all. It's just that, right? And this was a problem. For some stuff, it's not really important. If you have a batch job, you probably don't care. If you have a web shop, then you care, because then if you click something and it doesn't work, then the customers won't be very satisfied. Okay, this is Stop the World. If we talk about it, then you know what it is. And now we have to talk about collectors. And I don't mean the collectors in the JVM. I mean the collector principles that we have, because we have different ones. First of all, there's a so-called non-moving collector, or mark and sweep. Probably all of you heard about mark and sweep. But the problem is, how does it work? Well, pretty simple. If this is our heap, and I try to make it as easy as possible, you see the gray areas. This is memory cells, let's say it like this. And if they are blue, they are referenced. That means they are live. There's some reference coming from a stack frame into the heap, so this is reachable. If they are purple, then that means it's dead, right? Reference is gone. It's still occupying some space here. If it has the little red square on the upper left corner, that means the garbage collector marked it as live, right? Because we have the tracing phase. That means garbage collector has to find all the live stuff and mark it as live. And then if there's a number inside, that means if you do a garbage collection and you have live objects, then after the collection is done, these objects survived one cycle, okay? So that means the higher the number, the older the object. Okay. Here you see what you will see now. So we just start, we allocate memory, and you see objects die, right? So we fill up the heap, take some time, and you see already lots of objects die quite quickly. And now when we fill it up, we have to stop the world. Now, stop, mark, remove, unmark, continue. You already see the problem, right? It's really cluttered, even after the first run. And it gets worse and worse. So in this example, it's pretty simple because every object that I allocate is one cell, but in reality, it's different, right? You have larger objects, then you need space that is continuous, and it gets harder and harder to find this space, which is the same reason why in Windows we did this defragmentation. It looked very similar to this one. So this is mark and sweep. You get the idea, and you get the problem. It's fragmentation, right? The good thing is we don't have to move stuff around. It's a non-moving collector. It's just filling up space, removing the dead stuff, continue. And this is the idea. Very simple. And it's not too bad, but if it gets larger, you can imagine finding all the stuff that has to be freed takes longer, because for freeing, we have to check every cell and check, is it live or is it dead? If it's dead, then I can remove it. But therefore, I have to go through all the cells. If the heap is big, it takes some time. Leads me to moving collectors, which we have two of. It's compacting and the copy collector. Let's start with the compacting one, which is mark and compact. And this is still in use in the JVM. So same thing. You will see it's exactly the same until the point we fill up the heap. We won't fill it up completely, because now we talk about a moving collector. That means we move stuff. We compact it, right? This is defragmentation. So let's take a look at this one, if it works. Yeah, so you will see we won't fill it up completely. We stop the world, we mark the stuff, remove the dead ones, and then we compact to the left side. So it will happen now. Stop, mark, remove, compact, continue. Right? So you see, it's the big advantage here is we always can allocate freely because there's nothing ahead of us. It's always free space ahead, which makes allocation fast, and this is what we are aiming for. Problem is, we have to move things. To move things, we need additional space on the right side. It's not in this demo here, but you get the idea. But moving things means if I move an object in the heap, I have to update the reference that points to this location, right? Which takes more time. And you need headroom, because if you would like to copy stuff and compact, you need some free space where you can copy things first and then you copy back. So it's a lot of things going on here. That leads me to the next one, which is the copy collector. And this is totally different now. You already see this looks different. We have two spaces. And they have the name to space and from space. And these spaces will toggle. So we fill up the to space first. We allocate in the to space. If it's completely filled, we stop the world. We mark all the live objects. And then we copy the live objects. And before we do that, we toggle the space names. So you will see the gray one will become the orange one. That means the from space will become the to space. And then we copy all the live objects to the to space. And because this is empty, it's directly compacting. Once we did that, we know that everything in the now from space is garbage, and we can completely wipe it out. We don't have to check if there's garbage in there. So let's take a look at this one. Okay. Allocating. You see objects die. Okay, we fill it up. Now we have to stop the world, mark, copy, remove the stuff, continue. That means this is automatically compacting, which is the big advantage here. So we don't need headspace in the area itself. We toggle again, you see. And that means we always can allocate fast. It's always compacting, and we only move the live objects, okay? Okay, one more time. Okay, that's it. Problem here is if I have objects that live for a long time, I copy them with every time I have to toggle. I copy these long-living objects. That means I have to update references all the time for long-living objects. It's not really convenient. The other thing is we need twice the amount of memory because we have to make sure that we have all space available. In the worst case, we have to copy the whole thing, right? So that means more memory needed and long-living objects are copied all the time. And this is the solution to get rid of this problem. It's the so-called generational mark and compact, or get generational collector. Who heard about generational garbage collection? Who understand how it works? It's easy. You will see. First of all, we have to talk about the so-called weak generational hypothesis. That only means objects die young. And that's a fact. It's not only in Java, it's in all languages. Just as an example, if you have a method, right, and in the method you define some variables, when you call the methods, you define the variables, they will be allocated on the heap. Once you return from the method, everything's garbage that you defined in that method. So these objects will be just created shortly, died directly afterwards. And this is what this hypothesis means, and usually it looks like that. So we have lots of objects that die very quickly, and then we have a couple of objects that live a little bit longer, and just a few objects, they live for a long time. So that means we have short-living, medium-living, and long-living objects. How can we structure the garbage collector, or better to say the heap, to work with this kind of behavior? So we create a so-called Eden space. The Eden space is not very big, because it doesn't have to, because objects die fast, or die quickly. So there we create objects, right, when we allocate memory. Then we have a copy collector, which is the so-called survivor spaces. That means we have a threshold. If an object was copied, let's say, more than 3 times in my demo, then I take the object and promote it to the so-called to-nerd space. The advantage is long-living objects just have to be copied maybe 3 times, and then I move them into the to-nerd space. And now let me give you a little bit of explanation about the spaces. When we talk about young generation, that's the stuff that is in the Eden space and in the survivor space. So this is young generation. And then everything that is in the blue one is old generation, long-living objects, right? And then we have a minor collection that is only working on the young generation. We have a major collection. This is in the old generation. If we do a full collection, then it's in both, right? And in my demo, we do a full collection. So this is in principle everything you need to know for generational garbage collection. The advantage is you take care about the fact that objects will die fast, right? So then, because the thing we are aiming for is fast allocation. This is the main thing. And we don't want to copy stuff a lot, because that means updating references. This is the main idea behind this generational GC. And the to-nerd space is, the reason why it is so big is all stuff that lives for a long time, we just put it there, and it takes a long time to fill it up. Problem is, once you fill it up, you have to do a garbage collection in the old generation, in the blue area. And that might take some time, because this is mark and compact in this case. So let's take a look at the demo. It's a little bit smaller, and you will see I will allocate an Eden, then copy stuff to the survivor spaces, copy collector, that will toggle. After 3 generations survived, they just will be promoted to the old generation. And then I will do a fast forward. You will see like a wavefront moving through the blue area, because even in the blue area, objects will die. So let's take a look at that. Okay, we allocate, we stop the world, mark, copy, clean up, continue. Always allocating in the yellow area, okay? We fill up the survivor space. Once it is filled up, we just toggle, copy back and forth. And you see when objects reach the 3 generations, or they survived 3 times, now I will promote them into the to-nerd space and continue. And now we go fast forward. And you see the wavefront on the right side. So the purple things, right? Objects will die even after some time. And at one point we have to stop and do a full collection. So we do a mark and compact in the blue area. So now it will take some time. I slow it down again. We mark all the live objects in the blue area. Then we compact it. Now we compact. And then we copy everything from the young generation into the old one. That's a full collection. Then we continue. So this is the idea, and I hope you get the idea how it works. It's not really that complicated, but this is how a generational mark and compact collector works. And this is quite good, but this is all serial. And this is very much simplified, because this is usually even per thread. It's quite complex in the JVM. That's serial. That means we stop the world, we do our garbage collection, we continue. What about concurrent collection? That means we would like to do a collection while the allocator is allocating memory, right? So we copy stuff around while we are still working with the stuff. And that's quite hard. So let's talk about concurrent marking, right? It's the tracing phase. The collector checks which objects are live and marks them. And we have some problems with this, because if we do it like that, we start, the square one is the stack frame. We start from there. That's the so-called root, where we start to follow the references. And we find the first object. We mark it as reachable. We can reach it. Okay, fine. And then we say, okay, it's live. Go to the next one. Now we are at the second object already, and suddenly, remember, we are concurrent. That means the allocator can now allocate memory and change stuff. So that means the application thread can decide, you know what, I don't need this reference. I create a new one. The garbage collector passed already the first circle and marked it as live. So he's not aware of the new reference, right? So he just continues and marking and reaching, okay, fine. So I'm done, and this one he doesn't know about. So how can we solve that? Well, there's something that is called barriers. Who heard about barriers? Read or write barriers? Okay, just a few. In principle, very simple idea. The idea is that it's a mechanism to put some code on every access of a memory cell. If you read it or write it, then before you do it, you have to execute the code. This is the idea. And you can already imagine the code has to be very efficient and fast, because if it's happening on every read, then it might take some time, right? So it's used to keep track of intergenerational references, for example, and also to synchronize between the mutator or the allocator and the collector. So one thing you have to keep in mind, if we see how it works in the JVM, then usually we have 75% reads and only 25% writes. Creating a read barrier means it has to be very efficient, because it will be executed quite often, right? So this is something that might be interesting. Okay, so if we use it, then it works like this. We start again, and before we access the cell, the JVM will install these write barriers everywhere. So that means the collector just reach it, okay, it's all fine, reachable, I mark it as live. So the same situation now. And now the application thread decides, I remove this area, this reference here. And what happens is that the write barrier, the code that will be executed says, okay, if you remove a reference, we mark this memory cell that was referenced in any way as reachable. Only reachable, not live, right? And so that's all. So the collector continues, and same as before. But now, once he finishes it, there is a so-called remarking phase. So in this remarking phase, the collector now only looks for these reachable cells that have been marked by the write barrier. And then he marks this one as live. This is how you can do something concurrently by introducing a so-called remarking phase. It's an additional phase where you just look for the reachable cells in this case. So it might be too complex, but just keep in mind, barriers are good if you have to execute some code before you read or write to a memory cell. Okay. A concurrent copying, this is a different story, and you will see why. So we have our object on the heap. It has a header, we have some data in there. You see it's referenced by stack frames. They all point to this object. Now if we do stop the world, what we do is we stop the world. No application thread is working. Now we copy the object to the new place, like for the compaction, and then we update all the reference by installing a so-called forwarding pointer in the header, and then we update all these references to the new location, and once we are done, we just remove the stop and continue working. Done. Easy. But this is now concurrent. That means we don't stop the world anymore. So how to do that then? So that means we have our object, we just copy, we don't stop, and what happens now is we start updating references. And suddenly, in this phase, both objects are reachable, right? So that means you have one thread that can come from the one side, access this one, and the other one can access that one. And this is the worst thing that can happen, because both objects are live on the heap, reachable, not the best situation. So how to get rid of this stuff? Well, there's another idea how you can do that. And this is a so-called Brooks pointer. So what we do, we install the Brooks pointer on top of the object, in front of the header. And it's a forwarding pointer, and it points to the header itself, right? So this is easy for now. And that means all the references that are pointing to this forwarding header, going to the object, all fine. So now we take this object and copy it to the new location. And before we update the reference, right, we install the forwarding pointer in the same way. It points to the same header. And then what we now do, this forwarding pointer now will be pointing to the new object. And then we update the references. Right? Now, if we now update references, every thread will only access the correct one and not the old one anymore. Right? This is the idea behind concurrent copying if you use a so-called Brooks pointer. This is used in the Shenandoah collector, for example. And then once we are done, this is another thing you have to keep in mind. When you copy stuff, you need to keep the old one as long as you didn't update all the references. Once you updated all the references, then you can get rid of the old object. Right? So that means you need more space when you copy stuff. Okay, that's concurrent copying. And now let's talk about collectors in the JVM, because we have different ones. We have, for example, serial, which is one of the oldest collectors. And I try to put all the information for each collector on one slide, because otherwise my slide deck would have been 270 slides. And this is just 160, so it's fine. We have 50 minutes, easy. This is available in all JDKs. This is only for OpenJDK. So is someone working on OpenJ9 from IBM here? Okay, because this is different. They have different collectors. It's a different implementation of the JVM. So you see, it's not concurrent. It's not parallel. It is generational. Heap size, small to medium. You should choose it if you have a single core system with a small heap, if you have no post-time requirements, and it's best suited for single-threaded applications, development environments, microservices on small nodes. There's one thing you have to keep in mind, and this is especially for all the people that use the default collector, because that means you don't specify the garbage collector. Who's running on Docker containers, or containers in general here? Okay? Yeah, a lot of people. We are all Netflix. One thing that will happen if you don't specify the garbage collector, if the JVM decides that you either have just one CPU or you have less than 1.8 gigabytes, it will select this garbage collector for you. So that means you don't get the default, right? So if you stumble upon problems with small nodes and you think, why do we have garbage collection process, right? Because usually it should be G1. Then probably it's maybe you don't have enough memory or you just have one CPU. Then you get this garbage collector, the serial one. And the diagram just shows how it works. So it's application threads, we stop the world, one garbage collection thread, and continue, okay? Leads me to parallel, which is also called the throughput collector. Pretty much the same idea as the serial one. The difference here is that instead of using one thread for garbage collection, it uses mainly all available threads. And that means it's way faster. And throughput is defined by the time you spend in the application versus the time you spend in the garbage collection. If you use all available threads for garbage collection, means the throughput is quite high, right? So this is good for multi-core systems if you need peak performance without pause time requirements, because still the pause times can be longer, but doesn't have to be. It's good for batch processing, scientific computing, data analysis, and stuff like that. And still, it is generational, parallel, not concurrent here. This is how it works. Very similar to the other one you see. Because we have more threads available for garbage collection, it's faster, right? We have a higher throughput. It was the default collector from JDK 5 till JDK 8. By the way, who's working on JDK 8 in production? Okay, 11? 17? 21? Okay, 23? 24? Okay. Let's take a look at the next one, which is CMS. Concurrent mark and sweep. This is in principle the collector that I showed you, the generational. That's more or less exactly how it looks like, but in a more complex way because it's partly concurrent. It was available, because it's not anymore, from JDK 1.4 till 13. it was deprecated in JDK 9 and it was removed in JDK 14. So even if you're on 17, you can't even, when you use the switch, it's not there. You get an exception, so you can't use it. The idea was to get a more predictable pause time. So it should be less than 1 second. That was the idea, which is better because with the parallel one on the serial, it can happen that you have a pause time that is maybe 5 seconds. Then the next time it's 1 second. Then it's just a couple of milliseconds. So you never know. With this one, it was guaranteed it is less than 1 second, which is okay. That's not too bad, but it came with some problems, which is the reason why they replaced it with another one. And it was partially concurrent because it could do concurrent marking, right? And as already mentioned, deprecated as of JDK 9, removed from JDK 14 onwards. Concurrent marking, this is how the diagram looks like. I won't go through it because it will get more and more complex, as you will see. But you get the idea. And if you would like to have the slides, just ping me later on. I will send it to you. All right, this leads me to a new one, which is G1, garbage first. And this is the default collector at the moment. And this is totally different from the other collectors because this is a so-called region-based collector. Instead of having these huge chunks like Eden, survivor spaces, heap, to nerd space, the old generation, we now have these regions. And these regions can be at the maximum size is 32 megabytes. So no region is bigger than that. Can be as small as 1 megabyte, depending on the XMX setting that you use, like the heap size that you define. And as you can see, now all the regions are empty. This is how it would look like if they are filled. So we have an Eden region where we create new objects. Then we have survivor region, right, or regions. And then we have the to nerd regions. So in principle, the same idea that we saw with the generational collector, but now we split it into different regions. And that makes the whole thing more flexible. You also see the red one. That's the humongous region. It's huge, right? Because the object is bigger than half of the size of the region, then it becomes directly a humongous region, which is more or less old generation directly. So it will directly be copied into the old generation, won't move around. That's the idea behind it, because you don't want to move big objects around. Okay, I have a demo, and I defined for the demo 6 Eden regions. So I will generate stuff in 6 Eden regions. When I fill them up, I stop the world shortly, and then I take the 2 regions where the most garbage is in there. That means the most garbage means it's just a few live objects. And that's the main reason, because if I just have to copy a few objects, it's faster. Then I have 3 survivor regions. If they fill up, I promote them to the to nerd space. Let's take a look at that one. So we allocate, take some time. Objects will start dying. Ah, yes. And you can, the collector and allocator can allocate wherever he wants, right? So it's not really, a region doesn't have to be an Eden region. Once it's cleared, it can be then a survivor region or whatever. So you see how it works. And it's always this garbage first approach. Always take the regions with the most garbage and make them survivor regions, promote them to the to nerd regions, whatever. So this is the idea, and you see, and this goes on for minutes, you can see this is quite flexible, right? Because we always only have to copy small spaces. It's not really that we have to copy large things, or we have to, if we do the collection, we don't have to walk through a lot of memory to do that, because these regions are quite small, and we only select the ones that has the most garbage in there. So this is a totally different approach, and all the modern collectors that we have are using the region-based approach instead of having these huge chunks in memory. Okay. Yeah, G1, it has a pause time that is around 200 milliseconds. And it can even be faster, so you can tune it. There are a lot of switches for G1 that you can adjust it. It's good for heap sizes that are not larger than 32 gigabytes. So it will work, but the best performance is definitely around 16 gigabytes of RAM. That's the optimum. Up to 32 is still okay. If you get bigger, it can be slower. not really dramatically, but best performance you get with this heap sizes. This is, again, partially concurrent. It can do concurrent marking. It's generational, parallel, and heap size is medium to large. Best suited for mixed workloads, large enterprise systems. I mean, all the people that said we use the default, this is the stuff you're using, right? So this is the default collector at the moment. You see the diagram is already more complex, and it's, yeah, like I said, from JDK 9 onwards, it's the default collector, and it can also do concurrent marking. Okay, leads me to the next one, which is this one. Who knows epsilon? Yeah, because this is the non-collector collector, which sounds weird, right? It's a garbage collector that is no garbage collector. So why do you use something like that? The idea is, if you have a small service and you know exactly how much memory it uses at runtime, why using garbage collection? Because you don't need to, right? So this is the fastest thing you can use, but it's also the most problematic because it's so hard to predict how much memory you really need at runtime. This won't do any garbage collection. If you run out of memory, you run out of memory, right? It just fills it up and then it crashes. But if you really exactly know what you're doing, this is the fastest thing you can use. It's good for extremely short-lived jobs, or if you really need the last drop latency improvements or throughput improvements, it's a good thing. But believe me, it's hard. Especially if you have bigger services, it's really tough. But for playing around with it, if you would like, for example, to figure out how fast is your application code without having garbage collection stepping in, then you can try to use epsilon. All right, it's available from JDK 11 onwards. Yeah, it's only in OpenJDK. I think there's nothing comparable in OpenG9. And it's not for everyone. But for some people, it might be interesting to play around with it. Next one on the list, Shenandoah. Who heard about that one? Is someone using that? None? OK. This was developed by Red Hat. And this is, at the moment, the only non-generational collector. But with JDK 24, this will become generational. So then all the collectors are generational. At the moment, this is non-generational. So that means if it becomes generational, can be faster. Remember, if you have no generational collector, that means every time you need to do garbage collection, you have to do it on all the objects, right? On all the memory cells. If you have generations, then it means you create stuff in Eden in the young generation, and then you only have to collect young generation, which is faster, right? So it will definitely be faster than the non-generational one. It is good for very large heaps, more than 100 gigabytes. So just out of interest, who is using a heap around 16 gigabytes? 32, 64. More than 64 gigabytes of heap. Okay, who's using something like 2 gigabyte? 4? Okay, so it's more smaller heaps, right? So then this is probably not the right collector for you. These collectors are fully concurrent, right? So they can do concurrent marking, concurrent copying, and all these things. But they need more CPU to do that, and they need more memory to really shine, right? All these upcoming collectors that I will show you, it's more for really large heaps. Then they are really good. If you try to use them on small heaps, they will work, but not at the best performance. The reason is, if you do concurrent garbage collection, then it means you have, let's say you have 10 threads available for your application. This is if you do with stop the world. Then you stop the world, you use maybe all the 10 for garbage collection, you continue. If you use concurrent garbage collection, that means you have maybe 10 threads, but 2 of them will be used all the time for garbage collection. You efficiently just have 8 threads for your application. So you will always lose in performance if you use a concurrent collector. It doesn't mean it's a lot of performance that is used, but for example, Netflix, they switched to ZGC everywhere, and they saw a drop of 3% in performance. Sounds not like a lot, but if you think about what it means, to keep up with the performance, you have to spend 3% more in CPU and stuff, so it will increase cost, right? This is something you have to keep in mind. Okay, this is good for latency-sensitive applications, large-scale systems, highly concurrent applications. So if you have, for example, something like a high-speed trading system, then these collectors are really good. It's not available in Oracle JDK. It is available in OpenJDK. Right? There's a difference, but just to be aware. If you are an Oracle user, then you won't be able to use Shenandoah. Like I said, throughput is a little bit reduced because of concurrency. And this makes use of a load reference barrier, so which is a read barrier here. Which leads me to ZGC. Who's using ZGC here? Okay. Again, a regional collector. It's more or less like this structured, so we only have young and old generation, that's it. There's no survivor spaces here. The rest is very much the same as we saw before. This is for even bigger heaps. It can handle up to terabyte size heaps. And I won't go a lot into detail with this collector because the next one that is on my list is more or less the same because ZGC is a copy of the next one. Which means everything I tell you for the last one in the list, it also applies for ZGC. So it might become the default collector in the future. I'm not sure about that, so this is just guessing. Non-generational version will be deprecated, and I think it will also be removed in JDK 24. So there was first the non-generational version, then they came up with the generational version. Now the non-generational is deprecated, it will be removed because there's no reason to keep the non-generational. Okay, this is the last one, which is C4, concurrent continuous compacting collector. And this is one that was invented by Azul. Sorry for the pitch. But ZGC is a copy of this one. We did that more than 10 years ago, and it's only in our own JVM. And it's everything that is in ZGC. For example, they name it colored pointers. We name it loaded value barrier. It's the same thing. It's the exact same algorithm. The non-generational is a one-to-one copy. The generational ZGC uses a write barrier, where we use a read barrier. This is the only difference between these two collectors. If you are on Linux, then enable transparent huge pages makes a huge difference for the performance of the collector. As I said, this all applies for ZGC too. If we take a look at the marking phase, and again, this is the same, it's a little bit different here. So you see we have this LVBs or colored pointer. It's a read barrier on each of the memory cells. And we have the garbage collection threads, and they start marking live objects, right? So we go through this list, and suddenly the application thread kicks in and says, oh, I allocate this one. What now happens is the loaded value barrier or the read barrier or colored pointer, as whatever you name it, will lead to the fact that the application thread now will mark this object as live. It's not done by the collector, but it's done by the application thread. And then it will pass this information to the garbage collection thread. Right? So then the garbage collector knows, oh, this is a marked cell, so it's live. The difference here is that not the collector is doing it, but the application thread by using or by executing the code that is in the read barrier here. And that means the application threads and the garbage collection threads working hand in hand here. Right? And that's the big difference. There is no remarking phase needed in ZGC or C4. We just don't need that stuff. So that makes it faster, right? So because both threads can mark things. And the other thing which is interesting is so-called quick release. And that is if we have memory, if I talk about memory cells, it's all virtual memory. But at some point, there's physical memory in the machine, right? And there's some kind of memory mapping going on between those. So if we have these regions with the objects in there, then we see this is the virtual memory, and then the purple one is the physical memory. So once we start copy things like for compacting, we move objects from one area to the other. So we allocate also, again, physical memory. But instead of putting the information where we store it in the header of the old object, that was with the Brooks pointer, we just copy the information in an off-heap page, which is a totally different approach. That means the information where to find the new object is now somewhere stored in an off-heap page. And we do that for all the objects, right? So we move stuff around, And as soon as we moved it, we free the physical memory below it. That's quick release. Because we don't need the old object anymore. Because the information is in the off-heap page. Remember, in the Brooks pointer approach, we need to keep the old object as long as we copy and update all the references, and then we can remove it. Here, we can directly remove it after we copy it. That's tiny things. You might think, okay, well, what's the big difference? Oh, it's a huge difference in speed, right? So, and this is going on, and then we free all the physical memory directly, which means it's automatically available for allocation, which is the thing we're aiming for, fast allocation. Right? So quick release is a really good approach to do that. Okay, same as for ZGC, no difference, except it's only available in Azure Zing, it's only available on Linux, and the reason is that we also fixed the memory access in Linux because, and this is no joke, we have some piece of code which makes it literally 1 million times faster. And we proved that. So it's with our code, we can access memory 1 million times faster than standard Linux can do it. So this is the reason why we only have it available on Linux, where ZGC is not using this approach. Okay, but again, it's up for very large heaps. So the customer with the biggest heap is, I think, 21 terabytes. This is the heap, and we can do garbage collection with more or less zero downtime, so no stop-the-world pauses here. This is how it works. We don't go through the details. It's only in there. I told you all of that. The only difference here is that we don't have the problem with the drop in performance because we have a different compiler, and this compiler creates faster code so we can keep up with the performance without really spending more money on CPUs, for example. So the biggest question, which one to choose of all these collectors? Well, we have 3 criteria that are really important. It's throughput, latency, and resource usage. So you might think, okay, I would like to use the one with the highest throughput, shortest latency, and no resource usage. Well, it's not so easy because you only can choose 2 out of 3, right? So you can either say very high throughput and low resource usage, yay, but the latency won't be low. Okay, I say, oh, very high throughput, low latency, oh, you need more resources. Right? This is how it works. So you have to choose between these. To make it even easier, you can take a look at this diagram because it shows you if you aim for short pause times and you don't care about runtime overhead, you go to the left side of the diagram. If you say, oh, you know what? I don't really care about pause times, so it can be 10 seconds, but I'm really caring about the runtime overhead, so you go to the right side. And everybody else goes just in the middle. This is what you do. You use the G1, most of you, and it seems to work, so that means the JVM engineers did a good job. And the last thing I would like to show you is a little overview, which is this one, which contains more or less all the information that I found about the different collectors, so you can compare what is important for you, and then you have to make a decision. And just to make that clear, you don't have to come to me and ask me what is the right garbage collector for my application because I don't know. Right? You need to know that. And the way to figure that out is monitor your application, know exactly how much memory do you use, how is the CPU usage, and then what is the behavior of your application, what kind of responsiveness do you need, and all these kind of things. It's not easy to do that, but then you can tune your garbage collector to find the right one. And wow, I'm on time. So thanks for attending. If you have questions, I think we don't have time now, but I will be here. You can find me downstairs at the Fuji area, and then you can ask me whatever you like. So enjoy the rest of the conference. Thanks.